Welcome to a brief video on better data collection and analysis for driving semiconductor equipment reliability. It provides a more serious approach, suitable for serious problems. This is part of a series on AI-assisted reliability engineering. One of the prerequisites to advancing this effort is to move beyond general failures. Failures pertain to how a machine fails to perform its function. For example, a new car's door won't stay closed. Just using that level of information does nothing to enable a team to drive improvements with data. We need to go further, to failure modes, that is, the way it failed to perform its function, for example, the latch won't close. And then look at the wear factors, which refer to the mechanism which leads to the eventual failure mode, for example, the number of high-force closings. Unless you are going to go to this level, you just aren't being serious about it. For sputtering tools, if we just collect data on the number of plasma faults, we haven't gone far enough. We need data on the occurrence of specific failure modes, for example, arcing. A possible wear factor for this could be copper buildup. Of course, we can, and should, go deeper, to understand how that happens. Let's say we have 4 of the same machines that have the same average time between failures, or MTBF. We might infer that they are all operating alike. Averages are often misleading. A better approach, look at the actual times to each failure, each machine. You can start to understand more. For example, case 1 certainly looks different. Even better than just looking at the raw numbers. Put the data into separate frequency charts. Now you easily understand more. At the very least, you can see that all the machines are operating very differently, especially the first one. The next level of sophistication comes with making a Weibull plot. By the way, Weibull refers to the Weibull distribution. For this, we need to have the time, wafers, or other wear factor, to each and every occurrence of a specific failure mode. After applying a special calculation to each failure occurrence, the points are plotted on Weibull paper. The x-axis is on a log scale of the amount of time, or wear, etc. before the failures occur. The y-axis shows the calculated, cumulative probability of failure. If they approximately fall in a straight line, it basically means that the data fits the distribution. Weibull parameters include eta, also known as characteristic life. It is a location parameter, which shows where the plotted line crosses the 63.2% mark. Beta is the actual slope of the plotted line. That is, the rise over run. In this case, the slope is approximately equal to 1, which suggests that this is a randomly occurring failure mode. Unless it is a simple electrical component, it can suggest that there are a mixture of different modes present in the data. When the slope of the line is less than 1, flatter, it infers that we have an infant mortality mode, often caused by inconsistent assembly, quality, inconsistent installation, etc. Seeing this says that instead of just focusing on improving the average, the important thing to do is to find the source of infant mortality, and then eliminate it. Regarding PM, again, it makes sense to find and eliminate the source of infant mortality, and then think about preventive maintenance. When the slope of the line is much greater or steeper than 1, for example, 5, it indicates a rapid wear-out failure mode. This is typical for bearings, corrosion, or just end-of-life modes. Also, this case provides clear direction on the recommended frequency of PM or replacements. For the example, let's that we began with a slope of 1, indicative of a constant failure rate, with random failures. If we looked deeper, we may discover this data is actually a combination of different failure modes. Let's say we were able to remove several of them, and we end up with a steeper slope of 4. A useful question might be, at what point would we expect to see 10% of them to fail by? We go over to the y-axis and locate the 10% cumulative probability of failure, trace it over to the new plotted line, and then trace it down to the x-axis. We see that we can expect that approximately 10% of them would fail within 2,200 hours. You definitely won't get that kind of insight by using MTBF. Here are a few of the other valuable things that Weibull can do for you. How many machines should I test, for how long, without failures, to be 90% confident that we eliminated a failure mode? Based on the Weibull charts for different failure modes, what is the optimum number of spares we should keep? Based on this analysis, could I afford a 3-year warranty? After an upgrade is developed, how many of these machines will fail before we get the improved parts out to them? What is the probability of this type of safety incident occurring in the next 1 year? With this modification, how does that probability change? Fortunately, we can use AI tools and other free Weibull analysis software to assist in the entire process. After going through the training, you may need to refresh your memory when you are ready to use it. For example, you can ask, how do I decide if Weibull analysis is a good approach to use? What kind of data will I need? What are the Weibull parameters, and what do they mean? Analyze this data for me. How should I interpret this Weibull plot? How do I use this to determine the optimum levels of spares we should carry? How can we efficiently test whether our upgrade has really changed or fixed the issue? Hopefully, it is now obvious to you that this represents a more serious approach to collecting and analyzing data to drive improvements in reliability, productivity, and output. Here are additional information and training opportunities. Other brief introductory videos, like this one. Overview, discussion with leaders. Awareness and/or brief training for a larger group. Training classes and workshop sessions. Pilot projects. Individual coaching and mentoring. These presentations, workshops, mentoring, and consulting services can be done online, in person, or in a hybrid format. They can also be held off-site or on-site. We look forward to hearing from you soon.